Our next speaker is Matthias Schonlau. Matthias is a professor in the Department of Statistics and Actuarial Science at the University of Waterloo in Ontario, Canada. Prior to his current appointment, he held positions at the RAND Corporation, the National Institute of Statistical Sciences, AT&T Labs, and the German Institute for Economic Research, DIW. Matthias is a fellow of the American Statistical Association, and he has published many academic papers. His research interests are at the interface of applied survey research and statistical learning, in particular, coding open-ended questions. His talk today is on that topic exactly, and is entitled Coding Text Answers to Open-Ended Questions. Human coders and statistical learning algorithms make similar mistakes. Matthias, floor is yours.
Yes, thank you very much. Okay, is this visible?
Yes, it is.
Okay, wonderful. This is joint work with my PhD student, now graduated. So, open-ended questions give us text answers. They're often hand-coded into one of several classes or codes, or they're ignored. But if they're not ignored, they're often hand-coded. And in recent years, there's been a bit of a trend to automate this hand coding, or to see whether this can be automated. And so by automated coder, I mean having a statistical learning model do that. Statistical learning is the same thing as machine learning in this context. But one question is whether the automated coders and the human coders actually find the same type of questions difficult to code, right? With humans here on the one hand and the other side models, maybe they have different strengths. And if they do have different strengths, then when they have different weaknesses, and maybe one can compensate for the weaknesses of the other. So I'm investigating this, or we're investigating this in the context of double-coded data. So in double-coded data, two coders independently assign a code, and well, when they disagree, that disagreement has to be resolved in some way. This could happen either by them afterwards sitting together over a latte and discussing until they agree, or maybe one gets a third coder to cast the deciding vote, or a third coder who is an expert and much more expensive or has no time and who resolves this then. So the resolved code we call the gold standard. I'm not saying that's a perfect code, but it's as perfect as it's gonna get. So, and the other observation I'm gonna make is that if the two coders disagree, then one of them does not match the gold standard. So one of them, by that definition, is wrong. We investigated this with 3 data sets. Because of time constraints, I'm just gonna zoom across them. Patient Joe, it's a hypothetical situation in the medical office, and there are 4 outcome classes: proactive, versions of proactive, counterproductive. Happiness, what aspects of your life have you considered when assessing your happiness? There are 10 classes, different kinds. That was asked in German, the previous in Dutch. Democracy, what do you think of when you think of democracy in Germany? And then there are 7 classes were also asked in German. All right, so the sizes of the data set range between 1,000 and 1,800 observations here. They have a varying degree of disagreement. So the kappa inter-rater reliability ranges from 61% to 93%, which is astounding. And corresponding are the percentage of disagreement, so the percentage of whether two coders disagree, range from 5% to 23%. So quite a range. For the learning models, the statistical models or machine learning models to work, we have to translate the text into variables. Or at least this is one dominant approach, and this is the n-gram variable approach. Just very briefly, if you have a sentence here like no vaccine, all is challenging, challenge. So we use variables that effectively count the number of times the corresponding word occurs. Challenging and challenge here go to the same root word if you cut off the ending. And that occurs twice. And you also have a number of words, 6 in this, 1, 2, 3, 4, 5, 6. There's a whole bunch of variations and details, but I'm going to skip that here. Now, when you go beyond linear regression and logistic regression into more sort of flexible models, then you have to worry about overfitting on the data. And the generally used trick in machine learning and statistical learning is to separate the data out into training data and test data. And you do anything you want to do to the training data. And then when you're done, you check how good the model really is on the testing data. We used two statistical learning models, SVM, support vector machines, and random forest. They are very, very different models. All right. So we looked at 3 data sets. And for each of the 3 data sets, we have 4 coders, 2 automated coders, the 2 models, and 2 human coders. The automated coders are here on the left 2 bars, and the human coders on the right 2 bars. And so you can see in all cases, the human coders have higher accuracy with respect to the gold standard code. So, but that doesn't mean that they cannot still compensate for each other's weaknesses. So how do we look at this? So for each coder, we compute the probability of a coding error for a given answer text. And we argue that if there is an increased probability for human coding errors, if that is associated with an increased probability for automated coding errors, so if for a given text, humans are more likely to make error than also computers or the models are more likely to make an error, then we infer that they make similar mistakes. All right, so that boils down to correlation in the end. So then the question is, though, how do we get these probabilities? And for these statistical models, that's actually quite easy, because the way a statistical model classifies something is, well, they look at the probabilities of each class, and the class that you classify or that you predict, that is the class with the greatest probability. So here in this funny example, 0.6 proactive, the other 3 classes have smaller probabilities, the probabilities sum to 1, then I would classify as proactive. If I have a model-based estimate that I'm 60% of the time correct, then I know I'm 40% of the time incorrect. So that's fine for the models, but it's not so fine for the humans, because the humans say, well, the observation is proactive. They don't say, well, I think it's proactive with a probability of 0.87%. Like, we humans just don't do that. And so to deal with this, we did the following. We aggregated the data into subsets, and the estimated error probability is then in the subset is the fraction of incorrect classifications in that subset. To give an example, here I have 15 observations, and they are classified into 3 subsets, A, B, and C. In this particular example, coda 1 has in subset A incorrect, 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 correct, incorrect. So 4 out of 5 incorrect, so 80% incorrect. For the SVM model, we have actual probabilities, and because I'm aggregating, I have to average over these probabilities. This is the error probabilities, right? So what I'm doing is I'm going from 15 observations down to 3 observations, 1 for each subset. Here's my 80% for coda 1, and there's the average for the SVM. Now, this is just an example. Of course, we had more than 3 subsets. We had somewhere around 30, well, I think it was a bit more than 30 subsets per data set. And we're proceeding now on an aggregated level for the analysis. All right, so I mentioned the increased probability of 1 error for humans going along with an increased probability for errors for models is going to go to correlations. And here is the correlation matrix. So let's just look at one of them, human to human, coda 1 to coda 2. Down here, democracy data set is 0.4. So if coda 1 is more likely to make a mistake, coda 2 is also more likely to make a mistake, right? And so if you look at the models, the SVM and the RF, we have really, really high percentages here. We have 95%, and this rounds to 1, and this rounds to 1. So if one model makes a mistake, the other one also makes a mistake, more or less. It is good news, though, that all of these correlations, the estimated correlations, they're all positive. So that confirms the, well, that confirms that indeed they make similar mistakes, right? And if you look at the probabilities, the correlations between the humans and the models, which are here in the upper right corner for each data set, they are much more in line with this 0.4 and the other values here than they are with the close to 100% among the statistical models. All right. Okay, so correlations look at pairwise similarities, and we can also look at all four coders simultaneously. And if you do that principal component analysis, we find that the first principal component explains most of the variation, and the first principal component for each data set corresponds to what these four coders have in common, because the interpretation is here a weighted average. So first component is what they have in common. The others are what distinguishes them, but they have far more in common than what's different between them. All right, conclusion. Statistical models using n-gram variables have higher error rates than human coders. The automated coders and the human coders tend to make similar mistakes. And two very different statistical models give highly correlated estimated coding errors. So that means unlike where for a human, where you want to have a second human, there's almost no point in having a second model because well, they give you kind of the same answer. All right, yeah, I have some references that concludes my talk.
Thank you very much, Matthias. Please enter questions into the chat. It's a very interesting talk. This is a topic that's close to my heart. I wonder if you can say anything about the types of misclassification or the types of disagreements between either human coders with each other or the automated coding systems with each other. Are some, first of all, I'm not sure what the range of disagreements, what the nature of disagreements might be, but are they clustering in certain, certain strings, certain types of string, or is it kind of like disagreement at random?
That's not an easy question. We didn't really try to investigate whether they cluster somewhere. We looked at examples of disagreements, and well, I mean, where do they disagree? They disagree where it's sort of not totally clear what the answer should be, and that's not necessarily a fault of the coder. That can also be, it can be just that the answer is a bit ambiguous or the coding manual is ambiguous to that, right?
Yeah.
Nonetheless, we thought, so the way this n-gram approach works, it goes off keywords. It uses counters or indicators of words that come in there. And we thought that might give it a different angle as to what it recognizes and what it doesn't recognize. But in broad terms, it doesn't seem to be the case. They tend to have difficulties with the same observations.
Okay, thanks. There are a couple of questions in the chat now. First, do you have a specific reason for using SVM, random forest, and random forest rather than other flexible models or boosting, for example, boosting, or as you said in the I think conclusion, models do not make a difference?
Yeah, so we only looked at these two, and it was Sophie's choice to use these two. In my experience, well, boosting would be the obvious third one. I don't believe it would make a difference. The random forest goes off trees. Support vector machines comes in completely different, sort of coming from optimization. Boosting is a version of using trees in a completely different way. We didn't pick them for any reason, and I don't think it would make a difference.
Okay. Next, did Ari understand you correctly that the Coder 2 correlated much higher with the models than with Coder 1?
Coder 2 correlated much higher with the models.
I looked at, you showed a correlation matrix, and
Yeah.
so maybe you can show it again. Maybe I've misunderstood.
This one here?
Yeah, this one. Yeah. So if I look at Coder 2, and then I look at the first panel, right? I see 0.88, 0.89, but then I see Coder 2 with Coder 1. It's only 0.29. Am I misunderstanding?
This data is a little bit different than the other two. So this is the data where I was the expert, so we ran this here in Waterloo. And this was unusual in that I tended to agree with Coder 2 more than with Coder 1. Might have been an issue with how much attention was being paid, or maybe the instructions weren't clear enough, something like that. So that's a bit of an anomaly here, and that shows out. The anomaly also shows up later in the principal components that I didn't show in detail. If you look over here, though, it looks exactly what you were expecting, right? I didn't want to exclude this data set simply because it wasn't perfect, so that didn't seem right.
Okay, yeah, oh, I see. Okay, thanks.
Yeah. Okay, thanks. So one more. What is your recommendation for coding open-ended data?
Do it. My recommendation would be, it depends on how many observations you have, right? If you have 400 observations, there's no point in playing around with this automatic stuff, because it's much cheaper and faster to just do it by hand, right? If you get in the range, definitely if you have a couple of thousand observations, and if you don't hate coding, and so you're somewhat not totally adverse to doing this, I would probably do a fully automatic approach, either that or do sort of a semi-automatic approach where you can actually let the computer tell you where the computer is very sure, and let the computer just do that. And then where the computer is less sure, then you let the humans do it.
Great. Thanks so much, Matthias. Really interesting stuff. Oh, quickly, because I think we will have time, one more question. Going from basic CART to fancier models can result in minimal improvements, yet such models are very difficult to explain to clients or implement. Any thoughts?
Yeah, I mean, that is the problem with machine learning and statistical learning, right? If it gets fancy, then interpretability hurts. So I don't have the silver bullet here either. I put it this way: if a CART model gave me the same result as a fancy model would give me, I would use the CART model, because if it gives me the same result, I may as well use something that I can explain. But the CART models are very, very unstable, and I don't think you're doing the client a favor by giving him or her something that they understand, but it is problematic, maybe, depending on the case, right? So, yeah, it's difficult.
Okay, thank you. So there's one more question in the chat, but what if there's time after the third talk, which I hope there will be, we can come back to that.
Okay.
So thanks again, Matthias.